Okay, so we've asked Grok now to take the code from above and modify it so that I can so that it can build S over C3 squared. But I wanted to do this in code. And I don't know what it's doing. It's thinking, it's trying to reason through these. And I want code. I'm gonna stop it. I want to take this code. So from this code. So I want to take that code. Take this code. And add and basically extend it to build to create. Using SymPy. I think I have to be a little more specific. And I think that's a mess of it's thinking it's thinking that I'm putting like a markdown or something. So while it's thinking, analyzing code requests, while it's thinking, let's go and look at the code again. So the relations to the extra special group. I know that I asked it yesterday to understand. There's a lot of things to unpack in here. Maybe I'll just do the quick answer because it's trying to reason too much, I think. But I want the code. Oh, okay, actually did it. Group potion. Okay. So it's doing. So relations S. Define the quotient by adding relations. What? What? I don't understand that. Verify the order. The quotient should be 3, isomorphic to C3. No, all right, but why? So why are we defining the quotient by simply adding relations? Isn't there a SymPy construct to do that directly? That's interesting. So it's actually adding simply like a okay, that's interesting. So it's it's literally just defining the quotient by adding two relations. There's a lot to unpack here. Z is central. I would have assumed then, yeah, quotient. Yes, thank you. Oh, there's a lot of background noise. Apologies for this. So the what does it say in SymPy? The F groups module, the F group class represents finally presented groups by quotienting a free group by the normal closure of a set of relators. However, there is no direct built-in method like quotient for a group on an existing F group instance compute quotient by a given normal subgroup. Instead, the standard approach to manually construct a new group that incorporates the original relation plus additional relators corresponding to the generators of the normal subgroup, effectively getting those generators to the identity sorry, in the presentation. This is equivalent to forming a quotient. I think that's, yeah, because the thing is, if I recall well, and maybe, oh no, there you go, that was a good answer. No, what happened? If I recall well, and maybe I can open a new conversation. So the thing is, I need to, so this is basically coding the solution. I'm gonna, if I open a new question here, and I'm, okay, so can you refresh, can you give me more details about quotient groups in group theory? It was something about restricting one group with a subgroup or something like that. There had to be, the groups had to be subgroups in order to do that, I think, right? The operation doesn't have, so what are the preconditions for a subgroup, or for us to be able to do a quotient? I think that's what was happening. Quick answer. Yeah, exactly. That's the thing, and you're doing that in order to simplify the group. So it's saying, given the group G with this was visited somewhere in one of the other things in here. So it's kind of doing mod something. Yes, that is why adding relations should actually could actually work. You're defining, oh look, actually you're right. I think that makes a lot of sense. Wait a second, I think if I go here, so that actually makes sense because hey man, what happened? What? I had the code before. Where did that go? Where did that go? I lost that. Where did oh, there you go. There you go. No, that was the original code. I lost the code. Okay. Can you reopen? I had that code here, right? So on. How can I open the code? Move to project. It's in the project. I wanna open. There should be a nicer way to open the code, like the code layer here on the side. Can you open the last coding block we were working on. Should have been an auto. Hey, hello. What happened? I'm gonna refresh. I think let me refresh. Yeah, now we go. I think that's where we had the code, I think. No. Response. Yeah, there you go. Okay, I don't know, it was a bit of a glitch, I guess. So this now makes sense, because actually now that I revisited that, doing the quotient is kind of doing like mod, right? So essentially what you're adding as a relation is just saying, out of the 3 generators, I equals 1, Z equals 1. Can you explain that this line of code? It's a list containing the elements y and x, which are generators of the free group F. In the context of a finite generator, adding a generator as a relator is equivalent to setting that generator equal to the identity. Okay, let's unpack this. So why does this make sense? Well, we know that's a number, like that's, yeah, they have 3 generators, right? That's true, right? So we've got 3 generators. That's how you define S. S is just it's just like the 3 generators, and then you have things like that. But then setting the quotient to y. Why does this y? So if you add the generators as a as a relator. What is a relator in that context? Has order dividing 3. The same with one, exactly. This is a commutative relation. So, okay, that's a commutative relation. That is a... Actually, those are the commutations. Okay, so essentially, you're doing literally, like, that's what, when, you know, you're doing this, in a way, the way this kind of is currently computing in my head is... you know, when I was saying that in modular arithmetic, you kind of have, you know, you do 1, 2, 3, and then you kind of have those rules where you essentially say everything else above that. So 4 equals 1, 5 equals, 5 goes to 2, etc., right? So you have that relation where you're mapping. In my head, like, I'm reading these like that, right? You're essentially saying y, so you're picking 2 generators and saying y is equal identity and z equals identity. Okay, fine. But okay, but how do you get to that conclusion, right? So why does, help me understand, why does the C3 quotient, constructing the C3 quotient, or the quotient with the is equivalent to setting one generator to the identity. Why? Because the quotient thing, so the quotient thing was about restricting behavior, right? Quotient groups in group theory. So structure of quotient groups, elements. Okay, so that's what I was missing. So the elements of G over H are the left cosets GH. Okay, yes. So that is equivalent to doing that. Yeah, now I remember. I was kind of going back to that. Yeah, that's what I was doing. I think I was doing that with you know, having those elements like these, and then basically saying, well, you know, you just kind of pick like pick the subgroup, right? There might be these three, and then you're kind of just, you know, you're just focusing on something like these. So you're essentially saying, what are you saying? So GH, yeah. So what are the elements? So what are the elements of I need to open the code again. Should be easier to find group quotient. There you go. So what are the elements of? Yeah, okay. No, wait a second. So what are the elements of F? So you've got three generators and you have these relationships. So you have I'm trying to understand that, okay? So that's why I'm like struggling a bit. So I'm trying to understand the reason of why that's what you do, because that basically pretty much feels like you're kind of programming the group, right? You're just saying, I know what I need to do. I need to kind of make the module, I need to simplify that and make it modulo C3 squared, or C3 twice, I guess. Not twice, but like, yeah, squared, or two times, right? The fact that it's a product, it's like you're doing this two times. So those are the generators, right? Those are the generators, exactly. Okay, yes. I think now I get it. So these are the generators, but then the elements of F. So if I define a group like this, how many elements does that group have? I guess that's the 27. That's the order thing, right? So because you have these, you know, x squared, x cubed, y, you know, you have all the possible combinations of these with three rotations, right? I think that's the order, right? Yeah, that's the order, right? 27? No, 17. No, 27. And what you're doing with the quotient of like C3, because C3 actually just has one generator. That's true. It's 27, and C3 has only one generator, right? But we're doing this twice because we're doing C3 times C3. So we're doing the quotient, applying it twice. So it has only one generator. And exactly. And so what you're doing is when you're doing the quotient, you're essentially saying that you're taking, and that is like, so this is these thing here in quotient groups is you're doing these. You're saying we're just gonna pick one element. Form a quotient entity. No, wait a second here. So you're taking each element. Maybe I'm just glossing over something, so I'll come back to it. But I guess you're just taking one element of. You're doing the cosets, and the left coset would be an element of G, right? Which is the one that we have 27 of, the element of G, and then pairing it with like the entire H, right? So yeah, so you're doing module H. So essentially, and then I guess you're focusing just on one of these. That's what I'm missing from that definition. So that's an example. G equals Z, the integers under addition. And H to be NZ, which is a subgroup of multiples of N. H is now the quotient Z over NZ is the group of, yes, so you're taking one element of Z and then just focusing on these, right? 0 plus NZ, 1 plus NZ. Okay, so it's the group of integers modulo N. Yeah, okay. Wait. Yes, that gets it gets abstract. That's the thing. It gets abstract, but I think I understand the mechanic of like where we've just done a modulo, right? So we are basically just have done a modulo and just said, yeah, and this makes sense in my. So the I'm trying let me try to explain why this makes sense. Okay, so we're saying pick this set, which is essentially it's got 3 generators. And that actually already even helps without having to understand how that structure really looks like. This is the P group thing, whatever, blah blah. It has the 3 generators with all the extra bunch of rules, but then you do a quotient over C3. Whether you can do that or not, that's another thing. I don't know, right? Because again, C3 should be like a whatever it was saying here, like a normal group or something. I'm not going to get into that right now, but you're basically saying we're doing a quotient over these, and the way that I interpret that, to me, it naturally feels like I can interpret that intuitively as I'm doing it twice, right? I'm doing a quotient and then I'm doing another quotient because of that product in there. I know that's not maybe obvious to everyone, but that's somehow the notion of a product is I'm doing something and then I'm doing and then I'm applying the same operation to that result. It's not an addition. It's like it's two consecutive operations, right? But you're carrying the result. So you're and then essentially that translates from a programmatic perspective. It kind of makes sense. So it translates into just saying, well, we're just gonna map each generator to the identity. So I don't know. I wouldn't have come up with this at all myself, but I understand where is this coming from, right? It's basically you're setting Y and Z to be the identity. And by doing that, you're essentially just focusing. That's how you're doing the modular. You're just saying, okay, everything that is happening with X and Z will just kind of, it's the same thing, right? It's identity. I don't know. It makes sense at an intuitive level. It's hard for me to explain my mental state right now. It kind of makes sense, but I can't yet fully give a full-blown explanation. It just, the pieces seem to match in my head. Because you're essentially saying Y is the identity, Z is the identity, and you're adding that to the relations, So essentially, you're making some of these things redundant, right? You're just saying, well, it's the same as just forget about y, forget about z. I guess we could simplify those relations here. And then, okay, now we need to check that it's isomorphic, quotient group order, that is isomorphic to C3. My intuition tells me, though, that if you have an array, a list of relations, so let me ask Grog these. If I have a list of relations, am I able to use SymPy to basically find an equivalent, shorter and simpler, like a minimal, like list of equivalent list of relations, because that's what should define the order, right? As well. This is out of curiosity, okay? As another way to prove that this makes sense. But okay, the code speeds out, like if I run this code, it's gonna speed out 3, which makes sense. Which means that we at least have proven that this is correct. So now we have this group constructed like these. And the next step is I want to construct these. Okay. Give me a second. Exactly. So now this means that if group wait. Okay, it doesn't have a group. You can manually adjust relations to recreate the F group to test equivalences. Okay. The orders match or using isomorphism tests if available. So how can I check for isomorphisms? How can I check for isomorphisms using SymPy? Because the order is one thing, but it doesn't have to maybe be necessarily correct, right? Use the order. Further checks, compute abelinization of each group. SymPy. Can you add? Okay, so coset table comparison, limited use. Can you add a few of these extra tests to the current code? I just want to run these and make sure that isomorphism is correct. And I see actually how has it done it in test 1 compare orders. Wait, why does it do these like that? No. Okay. Wait. No, I want to compare. So I want to compare. So what I want to compare is. I want to compare these. Sorry, my bad. I want to compare isomorphism of these and these. Yeah, where S is like 3, that's correct, okay. That's what I want to do. So it compares the orders, it does the abelinization, which I don't know what it is. Okay, I can come back to this. Expected output. Okay. Same invariance. Can I just run this code? Tuple out of index. But okay, so let's just make sure. Okay, let's just make sure that that then we can try to see what we have used to check that isomorphism. Again, it's not maybe very needed because we can assume it's correct, right? But it's the yeah. I wanna make sure I understand a bit more of these. But okay, I've intuitively understood what this is doing, because S has 3 generators, C3 has 1 generator, and we're doing twice the quotient. So you're basically doing modulo on 2 generators. So you're kind of cutting, reducing the set to just S3, right? And now by the only possible non-trivial action of Sx on D. Okay. But still remember that all we need to do is this product is on S, it's not on these, right? But the thing with the non-trivial action and inducing is that next step is try to find, and you know what I should do so I remember this always? Okay, did it actually run or what? Groups are likely isomorphic. Okay, great. I should have always a next. That's gonna help me go from session to session, I think. I should have a, how do I create a new here? So it's gonna be next steps. It's note to self. Next steps. Check. Study actions and study actions from C3 to D. Study actions from C3 to D. Don't answer yet. Okay, just so yeah, that's basically next. So I know where that's a good idea. Okay, cool. All right, that's so we've done a bit more on these code for that, understood these. I think recap that makes sense. And now next is we want to understand how do we find the action, why we need to do that, because we then need to do S D times S in partial product to define G. And then once we have G, I think we've solved half the problem, because then we only need to understand the KG thing and the fields and all this kind of stuff. Okay, we'll take it from there. Bye bye.